of a series of four talks. Yes, this is one of the four talks, and this is the third one. And the speaker today is Pavlos Kollias. So it's a great pleasure to me to introduce him. Pavlos is a professor at the School of Marine and Atmospheric Science at StonyBrook University, State University of New York, and has a joint appointment with the Department of Environmental and Climate Science at Brookhaven National Lab. He's also affiliated with the University of Cologne and McGill University, Montreal, where he was the Canada's research from 2009 to 2016. He completed his master's degree in environment physics at the University of Athens in 1996, and later he got his PhD in radarmeteorology at the University of Miami in 2000 under the great Roger Lermite. He's currently the director of the Center for Multiscale Applied Sensing at Brookhaven National Lab, where he's leading a radical, groundbreaking remote sensing program focused on research on radar technology, signal processing, and cloud and precipitation dynamics and microphysics. He's also a member of the Mission Advisory Group and Algorithm Development Team of the European Space Agency Earth Cloud Aerosol Radiation Experiment, EARTHCARE, Explorer mission. He's science team member in the upcoming NASA EOS and INCUS missions, and also is member of the science team of the Wyvern ESA mission. All these missions will have radars as key payloads. Today, he will provide his vision and perspective on the radar meteorology in the 21st century. We will have questions at the end. Feel free to write them in the chat. And without further ado, Pavlos, the floor is yours. Thank you.
Thank you, Alessandro. I'll try first to share my screen, make sure this works. Can you see my top title slide?
Yes.
Okay, can you hear me well?
Yes.
First of all, thank you very much for the invitation. It's a pleasure to be here. And I echo whatever you said about Frank, and my deepest condolences to his family and to the Italian community. I had the pleasure to meet him a couple of times in conferences, and I knew a lot of things about him through his professional career, and it's a tragic loss for all of us. So I have a quite comprehensive seminar covering a lot of areas with the title, some of you might consider provocative, talking about the radars in the 21st century. We're already here, but things are changing so dramatically that I feel that seminars of this type are important for especially young scientists. So this is an outline of what I will cover. I will talk a little bit about us and what we do, where we're coming from, what is the focus areas, what is our vision, what's our desires, what is our expertise, and the areas of science and applications we work. But then I will cover three areas which I feel you might find of interest. First of all, agile adaptive sensing, meaning interactive with the atmosphere. And then two key technologies, phase array radars that probably you have heard before, and it's something that is is going to enter the weather radar community in this decade. And I will finish with some mentioning of really the extraordinary growth of opportunities and systems that we see in space. And there are technologies behind all that, obviously. So the first, who we are. I will start with what are we trying to accomplish here. This is a complex diagram, but it gives you a perspective about the challenge. We're dealing with a very complex Earth system with an atmosphere, with clouds and precipitation systems at orders of magnitudes of scales, with processes that matter even down to the millimeter. And of course, frontal systems or tropical, extratropical cyclones of the order of thousands of kilometers. At the same time, in the modeling, you try to capture this breadth of scales, and that's quite difficult. And you can see from the observational perspective, different platforms, space-based. In particular, they cover the very large scales. Let me try to get my my laser here. Okay. Spotlight. Good. So here you can see the space Platforms, which I'm going to talk at the end of my talk, they cover, of course, regional and global scales. There's airborne and suborbital activities, which are associated often with the spaceborne missions. And of course, we have a lot of ground-based facilities, either for operational purposes or for research purposes. So this is what we're dealing with, and this is something that we're going to talk about, a vision that we share with the department chair, Alison Makominski, at the Brookhaven National Lab. So we are the StonyBrook and Brookhaven National Lab Radar Observatory. We are a fairly large team, and nobody is more important than Alessandro Battaglia, who you guys are very fortunate to have now in Italy at the Politecnico di Turin. He is the true leader of spaceborne radar, and not only in outside of, I would say, JPL. Effectively, he is one of the true knowledgeable people, both in the science, the application, and transfer, and now he's actually getting into the technology. So he is somebody to notice in Europe, and a lot of us in North America, we also have the pleasure of working with him. So for me, he's been a friend. I worked with him for 10 years, but you can see a lot of fresh faces with a lot of young students from the university side, which is always a necessary ingredient, and a lot of seasoned researchers, which actually complement ideally, provide their experience and share their tools and allow us to spin up activities fast. The vision obviously is to be a leader. To be a leader in what? In the next generation atmospheric observing system. So when you always talk about the next generation, it means that something of today is limited, and I will cover that, and you will see. Of course, many of the things we do are in partnership with the Brookhaven National Lab, one of the 9 Department of Energy in the US national labs that has thousands of researchers and a lot of resources to help our research. So I would put one slide about something which I find very exciting. We've been working lately on what they call urban observations. No environment is as heterogeneous, as complex, and as challenging as it is the urban environment, especially coastal cities. More than 50% of the population already lives in the cities. And you guessed that right. This is the least understood and the least observed environment. Typically, when we do studies for weather and climate, we try to go far away from population centers because we really want to study clouds and cloud systems in their pristine and unperturbed conditions. But now lately, especially in the US, but also in Europe, there's a lot of discussion, a lot of programs starting now on looking at how this complex microclimate system works. So we do a lot of work on that, and you see examples that we have mobile platforms with LiDARs, not radars, that go in very complex environment next to skyscrapers, and they try to collect wind measurements using LiDARs. Generally, we of course going to be working on all sorts of clouds and precipitation systems. We try to pioneer a lot of model experimentation techniques, what in the US we call them MODEX. And this is something that basically we come to an understanding that observations are limited, models are also very limited, and there needs to be a much closer collaboration between those two, and not just after the completion of an observational campaign. So let's talk about challenges. Clouds, you have seen them, you enjoy them when you go to the beach. They have a very sharp outline some of the times compared to the clear air. This clear air, cloudy air interface is very important to us, okay? Dry air entrains, depletes the liquid in the cloud, change the particle size distribution. There are theories that suggest that even onsets precipitation. But this interface, what are the scales of this interface? How high resolution my sensor has to be to detect that? That's not something which is something we can tackle today. Even aircraft that penetrate, they need some time to sample. So it's not that they can actually collect data every ultra high resolution, although now we have a few sensors, experimental sensors that do that. So how do you do that with remote sensing? Because aircrafts are not easy to find and they're very expensive to have in a routine basis. So here you see something we develop in partnership with Stevens Institute of Technology and Raymetrics, a LiDAR company in Greece. This is a one-of-a-kind system. The one which is in the photo is actually now housed at the Brookhaven National Lab. It operates at 532. but you see the range resolution is down to 5 centimeters. So this can be accomplished by actually having what they call a single photon counting system, which also time gating, which basically allows you to go to a particular part of the sky. Think that you have a classical laser system, vertically pointing, tells you exactly where the cloud base is. And then you go and you telescopic view and you actually collect data with ultra fine resolution at the interface. So we've been testing now this system and we do some prototype measurements. And that obviously will give you images like the one you see here, which is the first system was developed was a few years ago back from the Colorado University in Boulder. But obviously already much better resolution and even more refined in the future. You will see a lot of photos with a lot of young faces, a lot of young scientists that are working on that. And without them, nothing would be possible. And that's very important to underline. At the same time, we just completed the upgrade of our W-band radar, now which is down to 1.4 meter resolution, and is using also the quadratic phase coding. So why we developed this system, besides the obvious advantage of, oh, now you're going to be doing very ultra fine resolution in the vertical as well. Here is an image back in the days when I was a graduate student, actually just a postdoc. This is how the BOE ARM program that does climate observations for over 2.5 decades now. This is the critical mode, collecting data every 10 seconds. You can see how blocky the resolution of a fair with a cumulus cloud looks like. And here's my research unit when I was working with Roger Lermite in Miami. The only difference between those two systems, I was collecting data every 2 seconds, they were collecting data every 10 seconds. So increasing time resolution is important. It's like buying a high quality camera and compare it to something which is back from the 90s. So that makes an instantaneous improvement. So what we try to do with this radar now is not to improve the temporal, we try to improve the vertical. The vertical in both systems is about 30 meters. So now we want to go down to 1.5 meters or so. So I think we think also that will revolutionize the way we actually do the measurements, the refinement, of course, the lack of non-uniform beam filling, but also we think it will improve our chances of actually going after the microphysics and separating from the dynamics. And if you think that sounds like a very good resolution, look at this system. So this system is a terahertz, a true terahertz radar, operates at 680 gigahertz. The system now is also at Brookhaven National Lab, and I have students from StonyBrook University who work on it. This system was developed by JPL and its original Jet Propulsion Lab in Pasadena. Its original intent was to actually use it for screening passengers as they come in the airports, okay? So it has a phenomenal range resolution, down to 2.5 millimeters. It can actually practically separate the fabric of your clothes and your skin and what you have between them. So what we did, we decided to pivot this technology. Well, this technology has been developed in massive numbers for this kind of bigger markets like, airport security, to use it to see if we can actually probe individual cloud particles, even snowflakes. Because we do have plans to develop a large cloud chamber in the US. And part of the question of building a big cloud chamber, which is a control environment for experimentation, is do you have the instrumentation to actually measure what's happening in the cloud chamber? So we're very excited about that. This radar arrived a few weeks ago, and we plan to do a few tests this year. So all these technologies, most of these things are available outside of atmospheric science. And this is a theme that will be throughout the presentation. What we try to do is to use this. We don't try to have to reinvent the wheel, but to pivot this technology to atmospheric science. The argument here is that you can't be talking about climate change and the urgency of understanding and improving your predictability, but not putting at this challenge all the resources you can find. So technologists and scientists like me and Alessandro, we constantly seek to find what's the next technology gadget that can be really overcome a deadlock in observations and help our understanding. So here we're going to do one more deadlock. It's how you do agile adaptive sensing. So if you're familiar with atmospheric remote sensing, in practical, it's very boring. It looks exciting, but the moment you go to a field site, it's really very, very boring. Things are static, nothing is moving, everything looks up, sensors are collecting data, And you might get beautiful data like this one. You see, this is time. Effectively, you have a radar looking straight up. And as the weather advances over you, you see different parts. You see something which is low level with a flat top. Looks like something like rain, the drizzle is falling. A bigger, deeper system, higher values of reflectivity means ice particles probably falling. Okay. A LiDAR has a different view. Like our eyes cannot penetrate, of course, through optically thick medium. So when it hits the cloud base, it won't go through. But in ice, it will be able to go through better and probably detect where actually supercooled liquid is. Okay, so this is a complementary standard view and standard use in atmospheric science of a radar and a LiDAR. You put them side by side, you collect observations, and there's no temporal evolution here. Okay, so you're looking straight up. What you see, it's a snapshot. Okay, it's like you try to understand this cloud system, but effectively all you have is a snapshot. It's like somebody passes by you, you take a photo with your camera, you have to understand the life cycle of that feature, which is not how it works, correct? You can't assume that what's happening the first 3 hours relates to what's happening 18 hours later. The second thing, which is very challenging, although we put all these sensors together, radar, LiDARs, we do not really use them in real time for any advantage. What we do, we go home, we take our office, we take the data, we download it, we process it, and after you process it, then you harness the value of the synergy. So there's no immediate value in the synergy. But some of you might go to your car, and if it's a self-driving car, it has a camera, a radar, and a LiDAR, and they work with zero latency. They can drive the car relatively safely by combining this in real time. So this is a data-driven dynamic system. We have it in operations for vehicles, but in atmospheric science, which is so important, this is not really yet where we are. So in effect, the sampling and how we collect observation in atmospheric science and what the atmospheric state is, they're not tied together. There's no adaptiveness. There's no optimization of whatever we do. We just collect observations that we try to interpret them later. The same can be said, and some of you, I hope, they are radar meteorologists or you're familiar with radar meteorology, with weather radars. Weather radars spin and turn. They do have movement, correct? So they do capture, and you have seen animation. So it's more lively than a static view. But most of them, again, they have a particular way that they sample, and that's pretty much. And that creates some limitations, which I will highlight. There are only very few efforts. Actually, I saw Anthony Illingworth is attending, and his group there at Reading University and Robin Hogan, they work one of the few times where we actually saw a radar system being driven by another radar system, or at least aided in its sampling in this very nice experiment they did back in 2015 and 14 in the UK. But also we have seen examples in the US where we actually have what we call collaborative networks, so that radars can start to talk to each other. And of course, we're in the 5G era. This is obviously automatic. You have edge computing. You can do a lot of computations on the node, and you can actually do a lot of communications very fast. So where we want to go is from this image, which is what you have today, a snapshot, poor resolution in time, so you're missing a lot of frames, poor quality in time and space because you don't have the revisited time, but on the quality. You want to go to that. Okay, you want to go to the state where it's going to be the best possible camera for your observations. All the frames, same cloud, track the same cloud also, study the full life cycle. So why we haven't done that? Because we're using radar, correct? The radar we use has some very fundamental limitations. These radars are basically have not changed in one very important aspect since they were given as excess equipment to the weather community in the late 60s from the military. They have a big reflector antenna. And this big reflector antenna, it's on a big positioner. And once it starts spinning, creates very challenging conditions for you to have an automated repositioning or even consider to stop and start, because that also introduces a lot of tear and wear on the hardware. So you want to avoid it. Plus, there's a lot of conflicting interest. Most people like surveillance and a 360 view, and put equal attention to everything. Some others like me may want to focus on the same particular cloud, but you can't satisfy those two masters together with this particular technology. So you end up with something which is, for operational purposes, very limited. Every 4 to 10 minutes sometimes is the time that it takes to revisit, depending on which country you are, which operational network you use. But we came up with this idea in 2020, which is effectively a considerable expansion of what Stein was doing in 2015. Basically, we said, well, if we cannot do everything, but we want a radar to target something, we cannot afford to have the radar also doing awareness to figure out what's around you. Maybe somebody else can tell us what's happening around us. So what we use here, we use the GOES satellite. Okay, we have geostationary satellites in Europe as well. We GOES surface camera, we use model output, we use everything available. We use the operational weather radars that are in the US. So we use all that data, we process them with almost zero latency because the data these days are available on Amazon services or the EARTHCARE servers within 10, 15 seconds after the acquisition. You can quickly process them, quality control them, get a much better understanding, more comprehensive understanding of what's happening in the atmosphere. And then you can steer your research sensor to go exactly where you want it to go without losing time to figure out himself what's around him. So you're saving time. So your reflector doesn't have to do a 360. You just tell it that second you go there. So this has been an expansion because now we use radar and non-radar data. We can use lightning from space or lightning from air. So if you want to study lightning, the lightning will go direct to the position and the radar will go and sample where the lightning is. Or you want to study the coldest cloud top, the highest, most severe weather. Well, there's nothing better than the GOES satellite to give you the cloud top height. You can't rely all the time on the radar to do that, either because of sensitivity or limitation of the sampling. So this is a very interesting paradigm shift on how to really create a more complete awareness. So here an example. So we're using satellite image here. You can see this is the channel 2, which is the red channel. And you basically see salocumulus cloud. This is the salocumulus cloud. The satellite's been used from one frame to another to figure out which way the clouds are moving, which is this line. Then the radar, which is sitting here, which is a state-of-the-art cloud radar, is being told, go there, sample. The radar goes and samples, and the boresight camera, which is on the radar, it can actually lock on this cloud, so does the fine-tuning as the cloud comes by. That could not have been before possible because cloud radars to be able to do a 360 takes minutes because of the type of beam width and other limitations. There's no way that the cloud radar could actually do the surveillance, then stop and track a cloud. By that time, the cloud would be over. So this is a breakthrough because this is automated and you can see cloud evolving from different stages. You can see the azimuth is changing because the scanner is moving as the collection goes by. Okay. So we're going to do this exercise. We'll be doing that in Houston with a much bigger radar, a big precipitation radar, a C-band like the one you have in Italy for the weather service. And here is how it works. The next rad, which is the one that the weather service has, tell us what the clouds are. We use also the GOES, not seen here, shown here. We figure out which cell we want to track. Let's say this one. Then the information goes from Bernard, who does the processing, all the way back to the radar in Houston in a semi-real time, within 20 seconds. It's been told, go scan there, very narrow sector horizontally, and do a vertical cut. And you keep doing that, you can actually focus on the same cloud over faster temporal and much higher resolution and higher quality data. So here you overcome, finally, you might getting close to the film of more color, higher definition, more frames. But there's also technology comes to help. This is great innovation and helps to overcome some shortcomings, this MAS framework, but the phase array radars are completely a game changer. So what's a phase array radar for those who are not familiar? The main thing is that effectively, when you get a radar, most of you, if you want to see a radar, you probably think about the big parabolic reflector, a big reflecting surface, which effectively creates gain by directing the beam to a particular direction, okay? So no matter how much sophistication you put on your radar transmitter, your radar receiver, or anything else you have, your signal and your energy you emit or the energy you receive is as good as your reflector. Somebody throws a rock on your reflector gets deformed. That's it. That's your way you translate whatever you do with sophistication for decades, and you interact with the atmosphere. So the phase array radar is basically phased on using thousands of little transmitters. Keep it in a very simple language. Here we can actually change the phase of each transmit element, and you can change there the direction in which constructive interference happens. So without moving anything, by just shifting the phase, you can actually introduce steering. So this steering means that it's near instantaneously, you can go to any location you like. So this eliminates the problem of stop and start, accelerate, decelerate automatically. In addition, something which has not been explored fully, but with the next generation phase array radars will be available, is that you can actually change your beam. The beam can be a pencil beam, or it could be a big fan beam. And some of you who might be related with air traffic control or with military applications, big wide fan beams are very, very popular. So now in atmospheric science, can do quick search using a very big beam, not having to go every elevation step by step, see something of interest, sends a narrow beam. So all these things can be changing within microseconds in a phase array radar. So that unleashes a lot of creativity, correct? Now you can do as you like with no limitation from a positioner.
That could well have changed because the model was developed in 2017, 2018.
That could be a potential area, but I'd be surprised if there was a change in that.
Sorry, can you switch
Can
you turn your microphone off, please, all the participants?
Okay, so thank you, Alessandro. So, but when I entered this arena of the phase array radar, what was concerning to me that the debate, at least in this side of the Atlantic, is all about how much time will take, what is the cost, and how the radar will have to look like to replace the weather radar network in the US. But if you're familiar with the weather radar network in the US, the next threat is the state-of-the-art weather radar network, correct? So I think it's a high toll. It's the wrong question, personally. Why you start with something which you have to understand how to use it in the research is not proven as even as a technology to meet the standards that we need for atmospheric remote sensing, which is very different from military applications. Why the bar is so high for phase array radars? Why the question has to be, can they replace and when? And how many of them the operational weather radar network? So since I started working with phase array radars, I try to change and recast the discussion. Pivot the discussion from the operational needs, try to get excited the atmospheric community about how this radar can be used for science generically, for applications don't need to be matching all the specification requirements of the operational community in the US. There's actually a bulletin of the MS article that we are in the review that will be probably available by the summer that actually captures some of our thoughts on this. So in StonyBrook, we have a great partnership with Raytheon. Raytheon, of course, very well known for the radars and phase array radars, has given different generations of radars. You can see two versions, the Skyler 1 and Skyler 2. The Skyler 2, which is the lower one, is the one we have now actually on our track. These are dual pole, high quality dual pole actually, which is one of the big challenges with phase array radars, X-band system. And I will show you some examples of how to use it. So here, an obvious, again, image. On the right is operational weather radar network. This is the operational weather radar, which is just 20 kilometers from our site. And we're looking at the weather, which is also 20 kilometers from the phase array. So I'm not doing something unfair. Both of them are looking at exactly the same target. On the right, again, the weather radar, 360. And what you see on the bottom right is a reconstruction of the vertical structure that you will get from a traditional reflector radar after it does many revolutions of 360s at different elevations. So every nearly horizontal line you see on the top right is a different elevation. And this sloping has to do with the distances, how far away the beam is. So this is how the vertical structure in this line is being captured by a weather radar. And this is from the phase array. The phase array radar, obviously, we have tuned it to have higher spatial resolution, can capture better these nice gravity waves. But notice something interesting. This is the vertical structure. The vertical structure not only is better, easier to interpret it, it's been collected exactly the same second that the PPI, the horizontal structure, was collected. We were running effectively the radar, not even to do first do PPI and then do an RHI, like a vertical cut. We were doing a few beams there in the horizontal, a few beams in the vertical, a few more beams in the horizontal, a few more beams in the vertical. Simultaneously, we were pivoting where we were doing the same, the two planes. So that's a breakthrough, clearly, because this structure that you see on the bottom right, it's a reconstruction of the atmosphere, assuming that everything is frozen, not moving for 5 minutes. And that's really a big problem, especially for deep convection. Another cool application of the phasar radars, you can actually put them side by side with high quality research radars with reflectors. So you can see here a water spout, the vertical structure from a cloud radar, very nice, unique one. And you can see how the phasar radar at the same time was picking up a lot of couplets and a couple of water spouts in the south shore of Long Island. So I think it's great research. For at least 10, 20, 30 years, there will be a symbiosis between phasar radars and research radars, correct? Until we all get comfortable with one or the other, but why not have them always together if there are certain advantages from each individual system? And here's the last thing. So we were thinking, and this is a lot of credit to Ed Luke from Brookhaven National Lab for coming up with this novel idea. So you're thinking, how I'm going to use this phasar now that I don't have the antenna limiting me? What can I do with that? Okay, but if you look at how actually your own eyes is moving, okay, this is pretty much how your eyes work. You can see here the Nefertiti image, and you can see the dots tells you exactly what your eyes, as you look at the image, focuses. Your eyes do not spend equal amount of time in the whole image. They have a broad peripheral vision, but they also have this fixation and saccadic motions from one fixation to another, from one dot that you see to another. And you spend way more time in its fixation point than you spend in the translation. Okay, so actually that's what you see here is not the eye. This was actually our radar and how it behaves when it does phasar array operations. So we have a system that actually in real time, the radar itself can actually figure out where to look. And this is exactly how it jumps left and right, left and right. It doesn't even have to pick up the right cloud. It can do multiple clouds at the same time because of its speed, correct? Every time you see this movement, which affected our elevation and our azimuth, the moment the eye fixates in any location, at the same time, we'll do a cross up and down, left and right, narrow. So we feel that this kind of, looking at a lot of the, it's also computer vision, looking at the human vision, it's actually give us some ideas about how to use it. So we have this this algorithm, the SPARS, the saccadic phase array radar sampling that we have been working. And this is an image with Christopher, who's one of our graduate students. So that will be also tested 2 weeks from now. 2 weeks from now, my entire group will be in Houston, where we're actually using both phase array radars and smartly sampling parabolic. So we're gonna see how this symbiosis comes together for a very large field experiment funded by the National Science Foundation and the Department of Energy. Okay, I'm excited and mid-career. Hopefully the young students are excited, but let's go to space, because space has a lot of touching issues with a lot of us, especially in the audience. So I'll focus on deep convection. What I've mentioned before about fast sampling tracking applies nowhere better than deep convective clouds. Convection in general is very transient, changes dramatically. Okay, there's dynamics, a lot of change. The image you see here is probably as best as we know updrafts in convection, basically through a cartoon representation. I would challenge everybody to come with better measurements of an updraft and downdrafts in deep convection. Something we can actually, it was not just a snapshot or an airborne view, but something we can really put models to the test. As a community, we are not there yet. A lot of the techniques we used in the past were not successful in capturing the dynamics of deep convection. And time is one of them. Focus on a particular cloud will help. But now I'm claiming that the space is the frontier to do it. So you want to capture that, which is within 30 minutes to see this rapid evolution. Okay. So CubeSats. A lot of great articles, couple references here, the paper from Graham Stevens 2019 and the paper from Milan in 2019 as well. Great articles to read and get excited about how the technology is transforming the way we use the space in these days, especially in our domains of atmospheric science. No greater example, demonstrated example than RainCube. So this is a very small radar. It's here, you can see it's full size deployable. The animation effectively will show you how the antenna was deployed in space. Actually, the antenna was stored together, and actually it's what they call a deployable antenna, mesh antenna. So it's actually, what that means that during the launch and during the ferry, this can actually occupy a very small space, okay? Effectively, if you take that radar and you bring back the solar collectors and the antenna, its size looks like the size of a Nike shoebox. Okay, so it's a very tiny unit and very effective. Great data was collected by that. So RainCube, which is basically a CubeSat with a deployable antenna and some other technological kicks that I will explain later, reverses a very interesting trend. We get typically a radar in space every decade. 96 Stream, 2006 CloudSat, 2014 GPM. We were expecting EARTHCARE, still waiting possibly 2023. Basically more than a decade per radar. RainCube came in 2018. The idea for RainCube was put together in 2014. But the trend that really changes is the size. GPM was much bigger satellite in space than TRIM. EARTHCARE, much bigger satellite than CloudSat. This is an unsustainable trend because these satellites become very expensive, and RainCube, in comparison, comes only with 12 kilograms, 6U unit, 0.2, 0.3 by 0.1 meters. As I said, a Nike shoebox. What that means practically is that you contact any agency that sends a mission in space for whatever reason, there's always free space. Can I put a few Nike shoe boxes in it? Free ferry, free launching, okay? And also brings the sizes down and the cost down. So here's Alessandro, and along with Bernard from McGill University, Alessandro and I have been working on, how long on EARTHCARE, Alessandro? We've been working since 2008, 9, 10, maybe 10, you 10, but maybe me from 8. We should actually feel fortunate because Anthony Inworth, who is here attending, he's been involved with EARTHCARE because he's a chief scientist of EARTHCARE, okay? So he's been involved since the late 90s, I suspect. So he's been waiting for 20 plus years for that mission to take place, all right? And here is this little group from JPL, 10 engineers put together, maximum age up to mid-30s. They came with a concept, paper concept 2014, they launched the satellite 2018, cost under $10 million. And now you have high schools in the US and many other countries building their own CubeSats. So now you don't even have to buy in from the whole community to everybody believe that your mission, the multi-million-dollar mission, is the best one. You can actually make your measurements at much smaller cost without really having to convince everybody about the utility. So I'm finishing strong here. NASA is doing this new mission after EARTHCARE, which is called Atmospheric Observing System, EOS constellation. It's a two-plane constellation. You can see a polar orbit and an inclined orbit. The inclined orbit has a follow-up to what JAXA is going to put together in space, which is a KU Dopplerized radar, Doppler in space at KU, which is a frequency that can penetrate precipitation. And here you can see another radar, W-band, K-band. So 3 radars, 3 frequencies, all Dopplerized. Doppler from space, a very difficult thing to do. Okay. So how this will happen? Doppler from space is very difficult to do. Anthony could give you a seminar about that. Probably it will not be a bad idea. But when you move with a 7.5 kilometers per second, let's say just that, with 7.5 kilometers per second, nothing else have to move for everything to look like it's moving relative to the radar, correct? So the motion of the radar, although the radar will be looking straight down, perpendicular to this motion, the finite beamwidth of the radar will create apparent motion. Everything will look like it's moving towards or away from the radar. It will create a lot of biases and a lot of challenges to correct. So how this mission, EOS, will actually do or dare to do Doppler, okay? They will rely on 3 things. First of all, deployable antennas. Deployable antennas means you can keep your beam width very narrow, even for low frequency. You can build radars can penetrate rain, like precipitation type of radar, without having to have a physically large reflector. You have a fully deployable antenna. The second thing, which is another breakthrough, is that they're using solid-state power amplifiers, which means now I don't have to get fixed on a particular way I transmit, like cloud.EARTHCARE has done. I can select short pulses, long pulses. I can go close to the surface, away from the surface. I can design a very, what they call a software-defined radio radar, which is the future. So there's a lot of flexibility there. The third thing, look at the day that thing was invented, 1952, is the displaced phase setter antenna, which to other communities like SAR or the military, that's well understood concepts. You actually putting two antennas, you're taking out the platform motion. In fact, the problem with a big, fast-moving platform is by the time you transmit the first pulse, by the time you transmit the second pulse, because you need two pulses for the motion, you have moved. So effectively, you have introduced Doppler. Here, the first antenna transmits. By the time the second antenna gets exactly the same spot where the first antenna is, you transmit the second pulse. Effectively, you did not move. So these three technological advantages are making this EOS mission to be in space. So we're going to be able to get things like that, and not over land only that you get with ground-based radars, over the oceans. For once, we'll be able to get this nice vertical cuts. Here's the model, reflectivity for those who are familiar. This is the velocity from the model, and this is what a W band, of course, not a lot of penetration, a KA band, and the KU. So you can actually, this is a paper that we published earlier this year that has these results. So finally, good Doppler from space everywhere. And you can sample thousands of convective clouds using a spaceborne platform, of course. So you thought that this would be great? There's INCUS. That was just announced back in November 2021. NASA selected INCUS, which stands for Investigation of Convective Apparatus. This is a quite cool idea. It's very cool because I'm involved with my institution, but let me tell you what is the novelty here. So using, again, deployable antennas, small CubeSats, 3 of them in a train. The first satellite flies here. The flight direction is this one. First satellite, 5 beams. 30 seconds later, the second satellite comes. And 90 seconds after the second satellite, a third satellite comes. So you have three radars in a train. It's a miniature constellation, okay? And they're going to go over the same exactly cloud. So they're going to capture the same vertical cloud structure convection in 3 different time instances. Imagine, before we even put phase arrays to have the ability to revisit the same cloud every minute, not every 4 to 10 minutes, we're going to be doing that in space. This mission is to be launched by 2026. So this is another huge breakthrough. Here's the leading institution, is Colorado State. The PI is Sunva Dehiver from CSU. And then it's a number of NASA centers and a few universities which are involved with that. Okay, so this is what you're going to be getting. Think about this is what's happening when you shoot ghosts, and the satellite will pass by and we'll see different snapshots of the same cloud. So you'll be able to see the ascent, and using different techniques, you should be able to capture something about the convective mass flux, which is effectively the product of the area of the updraft multiplied by the updraft strength. So you're going to show how effective are these deep convective clouds into transporting mass and energy upwards in the atmosphere. That's another animation that shows that in addition to the radar, there will be also passive radiometry. So that creates a complementarity. So this is the future. This is 2 teams coming together, very low cost. Okay. Last 2 slides. Again, you might think this is extraordinary compared to the pace we had. And here we have the private sector. The private sector, especially in the US, but this is not just for the US, has been really active in putting their own observational network. It's maybe the future. Maybe it's the future where the data comes. And the bigger question is, what do you do with that? So Tomorrow.io is a company that actually came out with a very bold statement a couple of years ago, and I think they have kept true to that. And I think they're going to start launching their Pathfinders in 2023 and the whole constellation of radars by 2024. the number is staggering. We're talking about 30 scanning radars in space by 2024. So that data, of course, is proprietary, probably used for their own numerical weather prediction model, but eventually past data will be available. You can imagine the myriads of applications that we could be doing to evaluate climate models, to evaluate numerical weather prediction models, to do fundamental research, doing the satellites. This is a breakthrough. It's compared to what me and Anthony and Alessandro have experienced with EARTHCARE. This is a dramatic change. And if I give these talks every 2 years, they will be changing dramatically in context, because the things we have added in this presentation since I gave it once 2 years ago is probably about 60% of the slides have changed. So finishing, last slide. In the 60s, we were given something that was a radar with a reflector. And we learned how to write textbooks based on the reflector principles. We learned how to sample the atmosphere and understand processes based on the reflector. Now, in this decade, that's a fair prediction. We're going to see the phased array radars coming up and the spaceborne radars introducing, revolutionize everything. Notice one trend. No matter which platform you picked, what becomes very apparent, the data sizes increase. So whoever wants to do radar meteorology applications has to be very good. All sorts of machine learning, AI techniques, big data manipulation now becomes very important to know how to address the size of the data, both from the ever increasing computational high resolution models, but also from the observations. I'll finish with my skepticism, because the Greeks have always very optimistic thing, but we also have some skepticism here. We can put all that thing together, and it's going to happen. It's a great data set. It's a golden age for the observations and for the radar in particular. Very myopic view of the observations, but in other areas, similar advantages happening. But understanding really the cloud systems and the precipitation, it's a far more challenging, much more complicated task. And with that, I will stop and thank you so much. Thank you again for the invitation.
Thank you, Pavlos. Thank you very much for your excellent overview. So I would now ask people from the audience. I mean, everybody can turn on the microphone and the camera and make a question, if you will. Maybe I start with a question, Pavlos. So you mentioned this adaptive scanning from the ground. We do have already electronically scanning radars in space. Do you envisage also to do this adaptive scanning from space sooner or later?
From space, probably through a constellation, most likely, because that would mean that you want to see multiple views of the same system for some applications. From one system also could be, if you want to stare, it's effectively you want to stare, you keep moving, but you want your beam to still focus on that. So effectively you can imagine what INCUS does, it could have been done with one phase array radar, correct? It could be just looking the same cloud as it passes through. You will still get the vertical structure. Given the spacing of a few seconds, you could actually have that with a phase array system. There's nothing that stops phase array radars being in space. There actually are some of them which are phased array in space.
Okay, there is a question from Mario. Mario, you can ask the question yourself.
Yes, thank you, Alessandro, and congratulations to Pavlos for his presentation. Very impressive. I would like to hear from him some comments about the limitation of phased array. So I'm not an expert, but from what I know, you have a limited range in azimuth of the scan, about 120 degrees. So probably you can avoid from the ground to making use the mechanical scanning. And the other limitation is that the beam pattern is larger when you steer the antenna at the side of your view. So in the light of the operational use, if if you have any comments or suggestion of that, or do you think that this is a problem or not?
Yeah, I give my perspective. This is a technological challenge well understood with the polarimetry, although I have to tell you, I don't sell radars for Raytheon, but the Skyler 2 version polarimetry is amazing. They have done very careful calibration of all these effects with the stretching of the beam width and the gains of the channels. It's very good. We see no azimuthal dependency on the polarimetry. Okay. If Raytheon has done that, I suspect something similar will happen with the efforts of OU and MIT Lincoln Labs. It's just a matter of time. What I'm trying to create is excitement to the research community. The operational community have their standards. Let me also give you my counter argument. What a 1 degree beam width requirement means for a phase array radar. When I have a parabolic reflector radar, it moves as it samples, correct? So what is your beam width? It's not 1, it's 1.4. A phase array radar doesn't move. I can stare. My beam width is 1 degree. So it's very unfair. When they say, for example, the requirement for his visiting is 4 minutes. That's for somebody that revolves on a static way. For a phase array, I can revisit something every 3 seconds. I can revisit the whole space every 2 minutes. It's a very different discussion. Unfortunately, it has been framed based on the knowledge of the people who are very familiar to operate the reflector radars, okay? Clearly, I think that the technological limitations you mentioned are a matter of time, okay? What I don't want to see is a missed opportunity because of us sticking very strictly to some operational requirements, which are basically the way you draft requirements. You tell me what you can build for me, then I would draft requirements. That's how it goes, correct? We don't want to use this limitation to limit the path of the phase arrays in operations, okay? The scan angle, correct, you're absolutely right. You can, with a phase array antenna, you can see 90-degree sector and 30-degree up. Our radar is both in a positioner for azimuth, very small movement, and for elevation, because I'm a big fan of high elevations. I just heard that the Weather Service now in the US believes that the future is face plane, but on a positioner, doing at least the 360. I'm a fan of no moving parts, and I thought they will go with the adoption of the 4 panels, which actually give the 360. Again, I'll tell you something else, Mario. A lot of the community they are very expensive. We can't buy them. That's not true. They're not as expensive as the thing. Personally, I can say that in 2 to 3 years from now, people who want to get phase array radars will be able to get phase array radars. And so I'm speaking to the research community who gets comfortable with a little bit of bias, if there's any, and it can do some cute applications I was trying to highlight.
Okay, thank you. Very, very clear. We hope in the future to see phase array deployed on the territory. Thank you.
Thank you, Mario.
Yeah, I see a question from Anthony. Anthony, you want to ask the question yourself?
Yes. Hello, Pavlos. The problem here is that if you speak to people at ECMWF who are actually wanting to use the data for data assimilation, they spend an awful lot of time. For example, when Aeolus, the LiDAR, was launched, the first 2 years they spent trying to work out the O-B stats and the complete small drifts of the antenna as it heated. And only after doing that for over a year did they have a positive impact. So this may probably to you, they sound like complete dinosaurs, but, and so the idea of CubeSats to them, which, you know, you send up and they last a couple of years, apparently at the moment, it takes them a couple of years to characterize the data so they know the statistics. So are they doing this wrong, ECMWF? Because this is what they were.
I'm pretty sure. One thing is for sure, ECMWF is not doing anything wrong. Let's put me on the record for that. Okay, let's be clear on that. Yeah. You know, it's a matter of perspective. When Aeolus is the only game in town, I can afford to spend also 2 years on that. It's also challenging. It's also I have time to spend on 2 years. If I had 50 Aeolus, the problem becomes a little bit different. Not because it's going to take me 100 years, but the utility of 50 Aeolus is very different. Okay, I can deal with big numbers. Big numbers compensate sometimes for some and make biases and understanding things easier. Correct. So I think there is value in big numbers. Now, big numbers without quality is useless because almost like putting noise in and expecting some signal to come out. Okay, so I want to talk about from this. I can't talk about the private sector, but from the agency's perspective, I believe that geolocation, biases, pointing is as good as it can be done. There is a fair understanding about what that means. So also the Incus is not a RainCube. RainCube was a demo, tech demo, under $10 million with no thermal shield or radiation shield in space, and survived for 2 years, 2.5 years, more than is expected. This Incus mission, it's $190 million. These are fairly well done, well built satellites. But ECMWF probably appreciates two things: coverage, which 50 CubeSats or 100 CubeSats will give you, and they appreciate also time resolution. Scientific community will appreciate time resolution. So I think there is, with proper data handling, the breakthrough in the data could be significant. But I agree with you, data handling is something that needs to be taken care of, and quality control.
Okay.
Yeah, and I think, yes, I mean, you are right, Pavlos. I mean, I think we will need both systems at the end of the day, because you will have, big systems well calibrated that will serve as sort of calibrator for the small system. So you cannot go with one and not the other, I think, in at least in the next years.
For at least 2 decades we'll go side by side, and I don't see a reason why not to continue side by side the systems together. It's the wrong strategy to say one or the other. It's the wrong strategy. The thing I want to say is, you believe or not, on phased array radars, there's another big synergy, convergence that happens between communications and sensing. Okay, if this is engineering school, you guys must understand that very well. Every 5G antenna is a phased array radar. You want to buy a phased array radar, go buy an Ericsson antenna. It's not going to be more. You put the backend, the software-defined radio with a Netus, which is $3,000 plus a programmer that can do FPGA programming. Here's your phased array radar. You have a partnership with a big telecommunication Vodafone in Europe. You can utilize thousands of cell phone radars already. So there's a big synergy now in sensing and communication that has to happen, because the communications are taking so much of the bandwidth that only in a collaborative share environment this will work out. We're not going to be able to operate the radars without RFI in urban environment in particular. So although we don't understand it, the technology is already there. Everybody can do phased array radars if that's the desirable. Not that it solves all the problems, but it can solve certain temporal issues.
Can I ask a quick question on the phased array? I haven't been watching this closely, but my understanding a few years ago was that it was okay to get the polarization on the bore site. But when you get off bore site, your ZDRs and ρHVs are degraded. Now, I haven't been following this. Has this been sorted, or is this still a bit of a challenge?
It's a very touchy topic. I can speak for the systems I have, that the polarization capability of the Skylar 2, which is still not the final product, which is Skylar 3, is extremely good. Compares and fares very well, has no azimuth biases. So it's a remarkable quality. Now, it's X-band, it's not S. It's not the big antenna. It's not the thing we're going to see. So there might be more things to do. Also, OU has come up with this cylindrical, which also shows very good performance. And then now working with a new prototype, they put together the ATD, the atmospheric testbed. that they put together with my MIT Lincoln Lab. So that would be very interesting to see how that performs also at S-band. But I think we're getting very close to addressing this.
That's good to hear that you think that can be sorted out, because I remember a few years ago there were a lot of people sort of questioning that aspect, but you're quite optimistic it can be sorted.
By nature, I'm very optimistic, but I will say that the biggest problem we'll have to figure out in this crowded future, because when you have when I look at happening in the US with the Amazon and Google packages and the drones and the big vehicles that put in space to move things, and that means there will be a lot of remote sensing at the 5G, 6G. The interference I see is the biggest issue. The dinosaur radar will die because of the interference. You won't be able to have a flexible waveform, flexible transmit pattern, adaptable to the environment. And that will be a biggest challenge. The phasar radar, because typically because of its beam, it can avoid interference, it can minimize, it can null interference, literally. So you have much more flexibility how to handle clutter and interference with the phasar radar. So if it comes from a particular direction, I can make to be a null and a minimum in that direction. So there's a lot of ways that this comes. The software-defined radio, wide bandwidth transmit, and phase array antennas is the only way to be able to realistically be a research platform, I would say 25 years from now. It would be very crowded for you to do otherwise.
Okay, I don't see any other questions in the chat, or if anybody wants to ask something, I think it's time now.
Are we having an espresso now? What is the protocol? Or you guys go for wine and cheese when you...
Very good talk.
Yes, excellent talk.
Was very optimistic. Yeah, I have a feeling. You know, people say we've been living in a fool's paradise in radar. We've been sending these single pulses with broadband, and no one's going to let us do that in the future. That's the threat, isn't it? We'll have to.
Yeah, it's a serious threat.
Yeah.
So the communication people are very serious. They're thinking about this problem much more than we think, because we feel entitled in some capacity. Correct, because also we never operated in a built environment very often, and the built environment becomes even more important to us, because that's where we live, that's where we do things. Correct, this is where we spend energy, we make energy and infrastructure. So operating in the built environment would change the way we do things. Security purposes would change the way we do things. So as I demonstrated with the terahertz radar for airport security, there's a lot of opportunities for research groups. Don't have to develop everything. They can young investigators in universities can actually build really novel systems and do a lot of cool science, because there's a lot of gaps, as I was trying to say at the beginning.
Okay, I think you have excited me. I hope that you have excited also the younger. I was already a little bit, but I think I get more excited looking at these things. Thank you very much, Pavlos, for your enlightening talk. And so I think we can close here after an hour and something. I thanks all the audience. I see many people from the US actually have joined. And for the Turin students, we will have another seminar next week, same time. I'll talk a little bit about still some of the spaceball stuff that will come up in the next years. So
as I said, you're the true leader on that. Thank you.
Come on. Thank you. Bye. Thank you, Pavlos. Bye.
Thank you.
Bye bye.